Hello everyone, this is Vasant, a nine-pointer at IIT Bombay from the Department of Civil Engineering. Today we are going to discuss a new topic called Poisson's Ratio. So I already said to you in previous lectures, E comma G K nu. These are elastic properties, right? Out of this, we already dealt with E, that is modulus of elasticity. G is shear modulus. It is also known as modulus of rigidity. Right? The K is known as bulk modulus. This is Poisson's ratio. So these four properties are material dependent. Okay. Means they vary their values depending on the material, type of material. So suppose if you take a bar with circular cross section and you go and apply P tensile force. So you know that it will elongate. So it will elongate, but you may notice it that it will also compress in lateral direction. So to elongate in this direction, it will compress in this direction. Right? So on applying tensile load, there will be elongation in axial direction, but there will also be compression in lateral direction. That is, you can do practical example if you take any type of material which easily elongates, like duster. So if you elongate that, then it will compress in lateral direction. So we defined stress in axial direction that as epsilon, that is equals to change in length divided by original length, right? But as in lateral direction also there is change in the length dimension. So we need to also define a strain term in lateral direction also. So this is similar to that epsilon dash is the lateral strain. See, if you see in this case, suppose this is of diameter d and length L, then epsilon will be L plus delta minus L divided by L. That will be epsilon by L. Suppose the final one is d dash, then epsilon dash will be d dash minus d divided by d. Okay, so this is epsilon dash. This is known as lateral strain. See, epsilon is positive, then epsilon dash is negative, right? So it is positive for tensile case. So this is for tensile case. So for compression case, epsilon will be negative, epsilon dash will be positive. Generally, this type of property is shown by metals, regular materials which we use in civil engineering structures. So this is in case of compression. But how much this epsilon dash will be, that will be determined by the material. So the ratio of epsilon dash by epsilon will be is equals to nu or mu, that is known as Poisson's ratio. So this value of Poisson's ratio is dependent on material. So it is a material property. Okay. So for a given material, there is a fixed value of mu. For a homogeneous and isotropic material, there will be fixed value of Poisson's ratio throughout the element. So for that, if you apply some axial strain, then lateral strain will be according to the axial strain, because the ratio of lateral strain and axial strain will be equals to Poisson's ratio. So this here there is minus sign because suppose axial strain is positive, then lateral strain is negative. These are general type of materials. So we generally want this ratio to be a positive value. So we keep a negative sign over here. So this lateral strain is negative and axial strain is positive. So finally the value will be positive for metals, general materials, any general materials, etc. Okay. So see, if you apply in axial direction, there will be strain. There is strain produced in lateral direction. So similarly, if you apply, suppose if you take a three-dimensional cube, and if you apply in this direction a compressive force, then there will be axial strain in this direction also. There will be longitudinal strain in this direction also, and longitudinal strain in this direction also, right? So it is producing strain in three directions on application of load in one direction, right? So this is about Poisson's ratio. Before moving ahead, we need to know about one particular type of materials. Those are known as oxidic materials. See, we generally said that Poisson's ratio is positive, right? So the value is positive. Right? But actually, there are also materials for which the value of Poisson's ratio is negative. The value of Poisson's ratio is negative. How? See, what is the formula of Poisson's ratio? Now, mu is equals to minus epsilon dash by epsilon. So for these type of materials, if you apply a tensile load, then there will be positive axial strain, means that will expand in axial direction, and they will also expand in lateral direction also, means that also positive. Or if you apply compressive force, then this will be negative. Sorry, this will be negative, and this also negative, means it will also compress, that will also compress. So how, see, if you draw a diagram, so this is, so if you apply load P, then see, because of load P, it should compress in axial direction, so it should compress in axial direction. Similarly, it also compresses in lateral direction. So this is also compression. This is also compression. Similarly, if we apply a tensile load, then it will go something like this. Okay, this is expansion. This is also expansion. So the value epsilon dash by epsilon will be positive, but there is negative sign here, so the whole value will be negative. Okay, the value of Poisson's ratio is negative. If you want to know examples on this, just Google this term oxidic materials. You will find bunch of material about this. Okay. So what is the range of Poisson's ratio? Poisson's ratio. See, we said Poisson's ratio is equals to epsilon dash by epsilon. But what is the range of this value? Means how much range it have. So Poisson's ratio का range है -1 less than mu less than 0.5. Right. So means I said that for oxidic materials, it should be -1 less than mu less than 0. Right? For general materials, the range is 0 less than mu less than 0.5. Okay, so if the value of Poisson's ratio is 0.5, then the material is said to be incompressible. Here, see, here there will be, you may wondering that if Poisson's ratio is 0.5, incompressible means there will be no deformations at all. No, no, there will be deformations. For rigid body, there will be no deformations. For incompressible, there will be deformations. But the change in volume will be zero. Okay, there will be deformations, but the deformations are such that the change in volume is zero. See, we said that for general materials, if we apply compression, in other sides, there will be tension. There will be tension means expansion. So one side compression, other side expansion. So the expansion, whatever value of volume increased in expansion will be nullified by the whatever value decreased in the compression, such that total change in volume will be zero. How this? How can we say that if the ratio is then the material is incompressible? That we will deal in next lecture. Next lecture, just next lecture. In next lecture. Okay. So with this, we end today's lecture. Until then, take care. Bye bye from 9pointer. Thank you.